In this lesson, we're going to talk about the laws of logarithms, or log laws. These log laws are related to exponent laws because of the close relationship that exponents and logarithms have. So if you recall, the product law in exponential theorem, or in our exponent laws, is that if you have a base to a power times the same base to a power, we can add their exponents together. Based on that exponential law, we can derive the logarithmic theorem that goes with it. So the logarithmic theorem is that log base a of m times n, so two numbers, is equal to log base a of m plus log base a of n. So for example, here we have log base 5 of 100 plus log base 5 of 1/4. We could combine those together to get log base 5 of 100 times 1/4. So because it's the same base, we can combine these together with multiplication. We then get log base 5 of 25, which is just equal to 2, since 5 to the power of 2 equals 25. So that's the first log law. The second log law is the quotient law. So in exponential functions, if we have a base to a power divided by the same base to a power, we subtract their exponents. Now in logarithmic form, if we have log with a base of a number divided by another number, we can split that up to get log base a of m minus log base a of n. So for example, here we have log base 2 of 64 minus log base 2 of 2. Because it's subtraction, we can then bring these together. So log base 2 of 64 divided by 2, or log base 2 of 36, which is equal to 5, since 2 to the power of 5 equals 36. Oops, this should say 32. Sorry. There we go. So log base 2 of 32 is equal to 5. And finally, we have the power law. So in exponential functions, the power law states that if you have a base to a power raised to another power, we multiply those powers. So that's similar here in that if we have log base a of m to the power of n, what we can do is we can multiply n times log base a of m. You'll hear me refer to this as bringing the power down in front. So the n comes in front, we multiply n times log a of m. So here, for example, log base 7 of 49 to the power of 5, we can rewrite as 5 times log base 7 of 49. Now log base 7 of 49 is equal to 2, so this is just 5 times 2, which is equal to 10. So we can use these log laws to do a few different things. We can either simplify logarithmic functions or we can expand them. So we're going to start by doing some simplification or writing as a single logarithm. So the first thing you always need to make sure of is that the logs have the same base. If they don't have the same base, then none of these rules apply. Next, any coefficients you're going to bring over and turn into exponents. Then you're going to take your positive logs, or things that are being added. Those are going to go into the numerator, and negative logs will go into the denominator because these, and you'll multiply them together because these are like ones being subtracted. So over here, we have 2 log x minus log y minus log z. Those are all base 10 logs. So the first thing I'm going to do is I'm going to bring the 2 up as an exponent. So I have log of x squared minus log y minus log z. And then this is positive, so it's going to stay on top. But then these are subtraction. So that's going to be like division, so those are going to go underneath. And we multiply them when they're in the denominator. So we get log of x squared divided by yz. The same thing is true when we have polynomials mixed in with our logs. So here we've got a natural log, so those are all log base e. The first thing we're going to do is bring these coefficients over to be exponents. So we have 3 and a half. And then this is positive, so x minus 1 goes in the top. X plus 3 to the power of 3, because we've brought that exponent over, goes in the top. And x squared plus 2 to the power of a half will go in the bottom since it's being subtracted. Over here, really similar, we've got log base 7, log base 7, log base 7. So the first thing we do is bring any coefficients over as powers. So this 2 comes as a power. What can also be helpful, if you want to, this is optional, but writing this as a fractional power might be helpful. Sometimes you might be able to do some simplification. So I rewrote that as 1/3. And then we've got a positive term, so x to the 1/3 is on top. Y to the power of 3 is being subtracted, so it goes on the bottom. And y squared is being added, so it goes on top. So this is what I was talking about with some simplification. Y squared and y cubed simplify to just equal y. So you get log base 7 of x to the 3rd over y. And then last one, again here we've got all these coefficients, so the squared has to come as a power, cubed, 1/4 and 2/3. And again, we've got positive and positive, so x squared, w 2/3 go on the top, and then y cubed and z to the 1/4 go on the bottom. Now, we can also do the opposite. So we can also take something like this and work backwards to expand the logarithm. So in the next example, we've got some like that. So here, you've got log base x of a times root c b squared. So the first thing you're going to do is anything in the numerator, you're going to add. So we've got log base x of a plus log base x of root of c. And then in the bottom, we've got b squared, so minus log x b squared. And then you need to bring your exponents down in front. So log base x of a doesn't have an exponent, so it just stays the same. Log base x of root c. That would be like c to the power of a half. So I've brought the half down in front. And then here, the 2 comes down in front. Over here, I've done it all in one step. So log a with the 2 down in front, plus log b times 2. And then in the bottom, we've got roots, which are both powers of a half. So minus 1/2 log c, minus 1/2 log d. And then down here, we've got a natural logarithm, but the same rules apply. So 2 ln x plus 3 ln y minus half ln z. So I've done the exact same thing there. So 2 different things. The first one we were simplifying, and in this one we were expanding. Then we can add one more step to this, and we can write them as a single logarithm, but then also evaluate. So in this situation here, we're writing as a single logarithm, so this is addition, meaning that 32 gets multiplied by 2. And here we get log base 4 of 64, which is equal to 3, since 4 to the power of 3 is 64. Over here, similar, we've got log base 3 of 108 minus log base 3 of 4. So 108 minus, divided by 4, is 27. And 3 to the power of 3 is 27. So that value is 3. Down here, we've got log base 10 of 4 plus log base 10 of 5. So 4 times 5 when we simplify, divided by 2. So this is log base 10 of 10. Remember, whenever you have log base of something to the same number, it's just going to be equal to 1, since 10 to the power of 1 equals 10. Over here, I've got exponents to work with, so I did that first. So I brought the 2 up, so log base 3 of 12 to the power of 2, minus log base 3 of 4 to the power of 2, That is 144 over 16. So we get log base 3 of 9, which is equal to 2. Here we've got roots. Now in this case, 175 over 7 can actually simplify. So remember, this is the same as this, which gives us root 25, which is just equal to 5. So log base 5 of 5 is 1. Question F is a little bit different. We've got 7 to the power of log base 7 of 3. So what I've said here is think of this as 7 log base 7 of 3 equal to y. So I set it equal to y. If we then change the power here to an x, we get 7 to the power of x is equal to y. So 7 to the power of this logarithm is equal to y. If we then change this into logarithmic form, we get log base 7 of y equals x. Well, x was log base 7 of 3. So here, y is just equal to 3, meaning this whole thing is just equal to 3. So you just have to play around with exponential form and logarithmic form. In example 7, you are given some values of logarithms. So what you'll notice here is it says log base a of 2. We don't know what the base is, but it gives you the decimal value. Log base a of 3 is equal to 0.5646, and log base a of 5 is equal to 0.8271. Now it's asking you to find the value to 2 decimal places for log base a of root 10 over 3. Now what you'll notice is 1, we've never done anything like this where we're trying to evaluate a log where we don't know what the base is. But also, when we do use a calculator for logs, which again we haven't done yet, you can't have an unknown base. So we have to use some other strategies to try and solve this. So I've given you a hint here to write 10 as a product of its primes or just as a product of other numbers. And what we're going to try and do is we're going to try to rewrite this logarithm, 10 over 3, in terms of 2, 3, and 5. So if you look here, we've got log base a of 10 over 3. Well, that's the same as root 5 times 2 over root 3. And we have values for 2 and 5 and 3. But the thing that's in the way now is the roots. So if we split this all up and we've got root 5 times root 2 over root 3, that means we have log base a of 5 to the half plus log base a of 2 to the half minus log base a of 3 to the half. So we take all those roots and put them to the power of a half. Notice that I added these two since they're in the numerator and I subtracted the third one. Now what we can do is we can bring these exponents down in front as coefficients, and we have values for log base a of 5 is 0.8271. Log base a of 2 is 0.3562, again with that coefficient of a half down in front. And log base a of 3 is 0.5646. So 1/2 times that. And then you can plug this into your calculator and you get a value of 0.31. So whenever you see questions like this, your goal is to rewrite the log in terms of the values you are given, and then you'll substitute those values in to actually calculate the value you're looking for. Now, finally in this lesson, we're just going to talk quickly. I mentioned before about using your calculator to calculate the value of logs. Now, on our calculators, we can only use or calculate log base 10. But if you have other logs that you're trying to solve for, so I'm just going to jump down for a second here. This is log base 2 of 3. So that means 2 to the power of something is equal to 3. And if we wanted to solve for that exponent, we have no way of doing that because these bases are different. We don't know 2 to the power of what would be equal to 3 without doing just a lot of guess and check. So we can use something called the change of base theorem. This basically says if you have log base b of n it will be equal to log n over log b. And then you would be able to plug this into your calculator. You're basically changing the logarithms to have base 10. So here, we would change this into log 3 over log 2. You could then put that in your calculator and you would get 1.58. This would be log 782 over log 5, and in your calculator that would be 4.14. And here, you could do these separately. So you could do log 8 over log 3 plus log 7 over log 4 to get this value. You could also do log base 3 of 8 times 7, and you would get log base 3 of 56, and then you could do log 56 over log 3, and you would get the same answer. So you could use your log laws there. And then finally, this is very similar. We have log base 7 of 6 minus log base 7 of 3 plus log base 7 of 2. It says write as a single logarithm, then evaluate. So here we've got log base 7 of 6 times 2, because those are the two positive terms, over 3, because that's negative. When you simplify that, you get 12 over 3, which is equal to 4. And here, we don't know 7 to the power of something equals 4. We don't know what that something would be. So we would use change of base theorem, log of 4 over log of 7, and put that into your calculator. So those are the log laws.